Thank thank you for the invitation to speak today. And I wanted to, I got to say continue here. I'm going to tell you a story that about some systems we've been working on recently that all have pi interactions in them. And it's really a tale of structured monolayers and multilayers and their interconversion and how grazing incidence X-ray diffraction has enabled us to discern the structure of these different types of films. So Benoit has already given the introduction to my group. So as she mentioned, we have two streams. One is sort of biomimetic and biointerfaces, understanding structure-function relationships in membranes. And we really have a couple of streams in there ongoing. One is looking at antimicrobial peptides and their interaction with membranes using both monolayers and bilayer model membranes, and as well looking at pollutant damage to, in particular, nanoparticle damage to lung surfactant. The other side of my group basically tries to take these properties and then apply them to design functional thin films, and in particular using lipids to create biocompatible coatings. But I'm not going to talk about that today. They are, of course, related because they're all based on lipid structure-function relationships. So I've not given this seminar before. It's a new topic with the most recent work we've been doing in our group. So I hope I can keep to time. So I'm going to move straight into it and talk a bit about pi interactions in membranes. And we started getting interested in this with looking at lipid-soluble quinones. So there's ubiquinone, which is coenzyme Q, and plastoquinone, which are both involved as two electron carriers in electron transport chains and as free radical scavenging antioxidants in membranes. So there are these pi systems that can give rise to pi interactions in membranes. And we got interested in this through a colleague of mine, Louis Cuccia, who had a similar or related quinone system. So this is a alkyl aminobenzoquinone, which is an interesting system because it has two chemically connected but electronically non-conjugated. So they're not aromatic rings. Let me just, so we have this conjugated system, but it is not connected to this conjugated system. And he studied them from, he's into chiral crystals and chiral self-assembly, and he studied them from a point of view of understanding the implications of charge-assisted hydrogen bonding in self-assembly processes. And what he was able to find is by doing some STM measurements on HOPG, that these achiral molecules are effectively prochiral in that when they absorb to the surface, lying down on the HOPG, they adopt what he termed an RNS conformation, which leads to either these zigzag or herringbone arrangements or these linear arrays on the surface. Now, of course, the difference, of course, when you put something into a membrane is that it would not be lying down flat, and it doesn't have this opportunity to maximize those hydrogen bonding interactions because, of course, it's going to have to be vertical. We wanted to look at these in monolayers, eventually looking at them in membranes, but I'm going to tell you a bit about what they do on their own in membranes, or in monolayers rather. So the first thing, this is the work of two undergraduates. I don't have a picture, unfortunately, of Escadar, but two undergraduates who worked for me quite some time ago. And they looked at these and they as you would do, you started with isotherms. We have a compression and an expansion isotherm, and we have this nice plateau that is conserved upon expansion, and they're really stable to quite high surface pressures. However, the Brewster angle microscopy was quite unusual. So the first thing is, of course, that it shows at 0 millinewtons per meter in quite large, high areas per molecule. So well away from that critical area where you start to increase the pressure. It shows the formation of these large condensed phase regions, very typical, I suppose, of any cohesive monolayer with hydrogen bonding or that tends to aggregate. But they're very striated. So you get this highly elongated striated domains showing a tendency for a preferred growth direction. So the strong head group interactions over line tension dominating. And what's interesting is that nothing really changes. We have areas of high density of these, areas of low density of these, but that doesn't change even after that plateau, which occurs around between, say, 12 and 18 millinewtons per meter. So nothing really changes, except that after the plateau, periodically as well, and at increasing as we go up in pressure, we start to see these very bright regions associated with the fracture lines where domains have come together. So we get these striated collapse material occurring on those phase boundaries. So the rigidity of the film seems to be forcing it into a 3D structure. Lipsometry we did at the air-water interface also confirms that we have a huge amount of condensed phase in our field of view, even at these high areas. So even way out what nominally should be the gas phase, we're already at a delta-delta value of minus 5.5, where delta-delta is proportional to the thickness of the film. And if it was a true gaseous phase, should be around 0. So Shirin, a postdoc that we had in the lab a couple of years ago, looked at these with grazing incidence X-ray diffraction. So reminder, these are the Brewster angle images that we're looking at. And we saw sort of all of these striated domains forming all the way up and including when we get into this, what appears to be a collapse area. So the first thing we notice is that below, we did the diffraction measurements, which we've done at BIN-WAS beamline. And below the plateau, we have, so at 5 millinewtons per meter, we have an oblique lattice. So if you look here on a different scale, you'll see that that is, these peaks here are in fact these two here. So it is an oblique lattice with a tilt of 28 degrees, no evidence of any head group organization, suggesting our head groups are fully hydrated. Once we get into the plateau and above the plateau, we see a coexistence of multiple diffraction patterns. So we have the same two peaks here, corresponding to our tilted phase, or oblique tilted phase. We also have, so we have, these are our 3 peaks for our oblique lattice. We then have a single peak here, which corresponds to a hexagonal lattice with 0 tilt. And then we have this pattern, which lies on the Debye-Scherer ring for a 3D powder, where the D spacing corresponds to about 3.9 angstroms, which is too small for our chains, and in good agreement with ring-ring, aromatic ring-ring spacing that's been reported. This D does not change, this pattern does not change throughout the compression above the plateau. So it's invariant and remains exactly the same positions. If we look a little more closely, we can do some AFM measurements on these patterns. And one of the things we notice is that these are not actually these striated domains are actually chains of much smaller domains that are connected together, but with very regular heights. Okay, and so I'll come back in a moment to the height analysis. Let's first look at the intensity along this Debye-Scherrer ring. So first of all, it's not continuous. So we have regions of higher intensity, which is suggesting that there are preferred orientations of the head group. And there is, of course, notably no Debye-Scherrer rings for the alkyl chains. So suggesting that this is then the head groups that are crystallizing with that D spacing that corresponds to pi-pi stacking, and that there are multiple preferred orientations. This is in contrast to, so we see no Scherrer lines here. We see no changes in the full width at half maximum, suggesting then that our alkyl chains are not crystalline, or at least if they are crystalline, then there's no correlation in position between our different layers. So if we go to the AFM, we again, so as I mentioned, there are some very regular height differences. And what we did is we plotted these. We did a histogram. And this, of course, is before I realized that Nanoscope would do this for me. So I counted 500 of those domains by hand to get these correlations. And we get these broad distributions centered around 3 nanometers and 7.5 nanometers. They're quite broad, which suggests that we have different varying degrees of either interdigitation or tilt or orientations or combinations thereof in agreement with the multiple orientations of our head groups. The full width of half maximum of these peaks also corresponds nicely to the size of the head group. So if we look at this, you would think that with this crystalline bilayer or multi-layer formation that we're seeing, that it might be, slow to, or rather non-reversible. But in fact, we are able to, this is fully reversible. So we see a series of compression expansion curves here, and we can go up and down this many times. I've only shown 3. There's a very slight change in the collapse pressure, but nothing else throughout this. And this plateau now, if we go back to the diffraction, appears to be correlated to a, if we look at this set of peaks, which is below the plateau, and this combination of peaks, which appears above the plateau, and then eventually this 3D ordering that appears, that these peaks correspond, and the plateau corresponds to a first order condensed to condensed phase transition, which is also confirmed, although I haven't shown it here, with the temperature studies, which show very little variation in the plateau position. So showing there's not a huge entropy change within for this transition. Such reversibility has been seen in Benoit's own work. And I'm terrible at pronouncing the name of this molecule, where they worked with silsesquioxane, which formed a triclinic organization of dimers reversibly and could be compressed and expanded, similar to our system, and which also showed the same sort of 3D structuring with preferred orientations along those rings. So as I just mentioned, there has been reports of monolayer to 3D crystal phase transitions. There have been reports of irreversible, non-crystalline multilayer transitions, and there have been stacked and interdigitated monolayers reported, as well as crystalline head groups. But we're reporting here, as far as we know, we hadn't seen other reports of it, a highly reversible multilayer formation where the head groups are crystalline with varying degrees of interdigitation or tilt. And we aren't unable to resolve that at this time. So in this story, that's where we are. We're now looking at, we've managed to structurally characterize the phases, and without the benefit of the diffraction, we would never have been able to work out what the BAM images were showing, because it made no sense that we could go up and down this isotherm with no evidence of a phase transition at all. And no evidence of coalescence. So it took the diffraction to understand this. We're now working with a study of C12 to C22 analogs, and then of course we will start mixing them with classical lipids and classical zwitterions, and eventually moving on to the metal complexation that my collaborator has worked on in the 2D. So this ties in. I'm going to talk now a bit about, it's a sort of a tale of two tales of pi stacking. So I'm going to talk a bit about the work that we've been doing with phenolic compounds. So phenols are prevalent in nature as tannins and catechol, flavonones. So they're known to bind proteins. So these bind to proline-rich and histidine-rich proteins. They obviously also exhibit, as did the previous lipid, antioxidant activity. Catechol is well known to chelate iron. And our original idea behind this project was to create a tannin-like surface in order to make a biosensor. So to basically try to mimic this tannin surface, or the presentation of this tannin surface, on a gold substrate for SPR, and be able to pull out very specific proteins. We're more in being, with the biophysical focus of my group, we're more interested in the protein binding capabilities of these films rather than the metal binding, but to pull out specific proteins that are histidine and proline rich. And these are prevalent in saliva, which makes them as easy for testing. So we designed then our phenol such that we have our trihydroxy phenolic head group. So this is basically gallic acid connected to a hydrophobic spacer and a thiol anchor, which we can then eventually attach to gold. And this is then the long-term idea, is that if we get the spacing right between these by controlling the spacing using a Langmuir trough, we can then get the spacing right for binding a protein. And we would propose to do this using a Langmuir-Schaefer transfer after we've pre-organized the material at the air-water interface. I'm not going to talk much about the transfer of these molecules today. I'm going to focus really on the structures that they're forming at the air-water interface, predominantly due to the strong hydrogen bonding and the strong pi stacking that's in the head group. So we know that the hydrogen bonding does play a major role in both in the organization and in the binding, which is why we need to be able to control that spacing. So ASME was able to show that using dihydroxy surfactants, that when you had the 1,3 hydroxys, that you got only weak binding to a ligand, in this case phosphate, because there was extensive intermolecular hydrogen bonding, whereas the 1,2 had intermolecular hydrogen bonding that could be disrupted in order to get a stronger interaction with the phosphate. So we started this work quite some time ago with Rolf Schmidt when he was actually a postdoc in my lab back in early 2000s. And he did some work with a double chain phenolic lipid called 1,2-dipalmitoyl glycerol. It had already been shown that it had a high gel to lamellar transition for the bilayers, and we were able to show that it had high lateral cohesion and rigidity in the monolayer. And we always attributed this to strong intermolecular hydrogen bonding, possibly pi stacking. More recently, Renaud Miquelette-Lamarche, who is a PhD in my group and has recently graduated and taken up a postdoc position in Calgary, worked with this molecule. So a much simpler version, octadecyl gallate, presents a very straightforward isotherm. We have a gas to condensed phase transition, and then very steep increase in pressure followed by a film collapse. And of course, these are just as rigid. You can see, because by the barriers compressing the film, we always get this measurement that we get this pushing of the plate out of the plane. So it's no longer vertical, which means we get this rounding of the isotherm because it's no longer accurately measuring the surface tension. At high molecular areas, yet again, we see that high cohesion that is that we saw with the previous system, and as we also saw with our double chain lipids. So, sorry, lost my mouse, which again, you get these rigid domains that are forced together. They don't coalesce nicely. You still see the residual areas. You see the collapse occurring on the grain boundaries where the domains have been compressed together. And these are so rigid that not only do they push the plate out of plane, the Willemy plate out of plane, they don't transfer well. So they actually break up upon transfer onto mica. So again, we turn to diffraction and to determine the unit cell parameters and the structure of this condensed phase. And a couple of things to note. So the first is obviously, so it's got two peaks. It's a tilt towards nearest neighbor of about 39 degrees. So they're fairly highly tilted. Couple of things to note. One is the very high position of this high QXY position of this peak that is closest to 0 QZ, and the associated A0 value, which comes out to 19.2 square angstroms, which of course is less than that for for conformational disorder or free rotator phase. And we did a distortion analysis, because you see that one thing is that is relatively invariant. The tilt angle is relatively invariant over a very wide range of pressure. So from 5 to 40, we vary by only 2 degrees in tilt. So all of this suggests, and this is the same, we also did this at 0 pressure, and it's the same unit cell. So all of this suggests that it adopts a preferred orientation immediately as it's spread on the isotherm. And basically, as you're compressing it, you're very little change to the tilt angle, which is really just you're basically squeezing out any residual gas phase throughout this isotherm. But all of this, especially if we do this distortion analysis, which is the sign of the tilt angle against pressure, we find that we have a non-zero value of the distortion at 0. And all of this tells us that we have a herringbone packing of this film. Okay, if we take a broader scan, what you'll see is this one is more evident. This is a little harder to see, but as you can see, it is there. We have 2 additional peaks, one at QXY 1.86 and one at 0.96, which if we move to now that we know it's a herringbone packing, if we move to a rectangular notation, can be indexed as the 1, 0 and the 1, 2. But notably, this peak here at QXY 1.86 has a much larger full width at half maximum. And it comes out to about, if you measure this, it's about 1.05 inverse angstroms, which correlates to about 5.4 angstroms, which is approximately the length of the head group. So all my other peaks, including this one here, all my other peaks have a full width of half maximum of about 0.28, which correlates nicely with a C18 tilted chain. So this led us to assign this peak to the head groups. Now, if our chains were herringbone, we would also see the peak at 1.86, but it would need to be out of plane. And we can't preclude that it's buried underneath, and especially with the other evidence we have that should suggest a herringbone packing for our chains. Obviously, herringbone packing has been reported for single chain surfactants, usually below room temperature or with much longer chains, so about C22 chains, suggesting that our herringbone packing is driven by strong head group interactions. Now, head group ordering has been, as I said, has been reported for fatty acid, molecular superlattices have been reported for fatty acids. Less common due to our often for systems though, such as this one that was reported by Gallard's group, where you have a large head group. In our case, we have a system where our head group size is commensurate with the chain size, and that's which we did not see when we did the diffraction on our double chain lipids. So that certainly plays a role in allowing these surfactants to get close enough together. Now, a herringbone head group ordering was proposed just based on space requirements by Pikert, who suggested that the chain cross sections allowed it to be in a hexagonal type of packing, whereas the head groups would be forced to organize in a herringbone arrangement simply because of their size. But that was never confirmed, and that was for a single hydroxy, not a trihydroxy version. So ours, we've been able to report assign the peaks and have evidence, physical evidence of such an arrangement for the head groups themselves. We've done some computational studies. I'm not going to go into the details. This is my collaborator is the computational chemist, that's Heidi Muchal, and Janet Gaba is the PhD student that we have working on this. She first, we've been working with quantum theory of atoms and molecules, so Qtame, to look at bonding interactions. First, simply trying to determine the correct model systems in order to reproduce what's been seen in microwave spectroscopy, which is this cone-shaped trimer. But interestingly, when we did once we determined the correct theory to use, and we moved on to a system in implicit water where we have our methyl 4-hydroxybenzoate, 42 of them, this is a top-down view, you can see that we are able to reproduce in the pi stacking is driving the head group arrangement. And if we overlay and look at the positions of this carbon here and map those positions, what you can see is that we're able to identify that the parameters here that we're seeing that appear clearly because of this ring orientation, this ring stacking, are very similar, even though this is also the methyl hydroxy, the monohydroxy, very similar to what we're seeing for our octadecyl gallate, which is the trihydroxy. And if you look, then from a side view, what you will see is again that ring stacking distance 3.1, 3.2 angstroms that nicely corresponds to the ring stacking that we've been able to see. So that allowed us to determine that what we think we have is we have a tilted chain system where the underlying head groups are arranged in this crystalline head group pi stacked system, which is herringbone. And so you have distinct organizations of the head group and the tail regions. They are, of course, commensurate with each other. And so the peak positions for the chains fall under where you would expect for the head groups also. Now, we've tried to tune, as I said, one of the things we wanted to do was, with our thiol version, was to space these, to space the molecules out such that we could deposit them and control the spacing for creating a biosensor. And as you saw, we weren't able to do that with our film on water because we were not able to vary the organization from gaseous all the way to collapse. We had exactly the same structure. We couldn't even vary the spacing or the tilt of the molecules. So one of the things we've tried to do is to tune the interface and tune the organization using charge repulsion. So we've started to try to change the pH to be able to deprotonate some of these hydroxys on our head group. Up to pH 8, which isn't shown here, the isotherms are identical to water. pH 9 and above, we see these shifts to higher molecular areas, as you might expect with some charge repulsion, and two distinct regimes forming. So you see that in the compressibility. So you see a distinct regime for pH 10 and below, and then a distinct regime for anything above pH 10. And we'll go through some of the what we think is going on in here. So again, we turn first to Brewster angle microscopy to look at the morphology. Again, we have those large regions of aggregated state. This is before the onset of pressure, and always here is after the onset of pressure. As we move from pH 9, water to pH 9, we see that we never fully coalesce these interstitial spaces, which we are able to fully coalesce. These will actually fully coalesce into a homogeneous film. And by pH 10, we see the breakup into small domains that form these chains. Again, not coalescing. They resist coalescence, which we presume is because the domains are now adopting a charge, and that charge repulsion is preventing coalescence. But suddenly that doesn't seem to hold when we get above pH 10.5. So we see again these chains forming at 0 millinewtons per meter, and a very low contrast film at pH 12. We resist coalescence here, but you would, from this scale at pH 11 and pH 12, it appears that they coalesce. So we turn to AFM to get a bit more detail. And this is what we see. So at water, this was these highly rigid films that unfortunately would always break up whenever we tried to transfer them. At pH 9 and 10, we see these domains forming, but they don't properly coalesce. You see the residual grain boundaries, you see the residual holes, which are from the interstitial spaces between the domains, and these resist coalescence. Once we get above pH 10, we originally did pH 11, and then because of the huge difference between these two images, we went back and did pH 10.5. What you see is highly oriented domain growth with dendritic structures. And again, this oriented growth, either with the dendritic structures or even with these long, elongated, striated domains, emphasizing that those head group oriented interactions are dominating over any line tension effects. And now we're at this point, we believe we're only a single, so singly deprotonated, not fully doubly deprotonated. As we go up to pH 12, pH 11 and 12, where we start to, again, induce more deprotonation, we see, again, that low contrast that we reported here for pH 12 is actually because we have these domains with these interstitial spaces that are full of nano scale domains and fingered connections between the domains. Now, if you take a close inspection of the pH 11, which I've put here on the right-hand side of the screen, you'll actually see that there are multiple phases present. Okay, so there are holes present. There is a phase here. There's a phase underneath, and then there is also a what appears to be some sort of matrix continuous phase. And again, we turn to the height differences, and a height analysis tells us a bit about those phases, but I'll come back to that. It's more telling when we look at the diffraction that goes with them. Okay, so okay, we'll mention them now. So the dendritic phase to the lowest phase, not the holes, but the lowest phase here is a nanometer. The intermediate phase to that low phase is about 0.7. So there's only about 0.3 nanometer difference between this bright phase and this intermediate phase. The depth of the holes is about 0.9 nanometers. So that tells us that what we think we have is two different condensed phases coexisting with a liquid expanded phase. So if we turn to the diffraction, again, let's go back to the water. We have the water phase here. Again, we have that same diffraction pattern, including the head group peaks. And that persists at pH 9. Despite the huge change in morphology, we have no change, absolutely no change in the diffraction pattern. So what that's telling us is, although the domains themselves are repelling because of an accumulation of charge, the structure within the domains is remaining the same. Now, once we get up above pH 10, then we start to see, as we said, we proposed increased deprotonation. We see the same peaks, much weaker, but we also see a new set of peaks appearing. This, we thought, well, the options are either we have impurities or this is a kinetically controlled process and it's just very slow to rearrange. So what we did is we waited 60 minutes and this is what we get. So these peaks that correspond to our original structure disappear and we're left with this new structure, which has no head group organization and is a standard sort of chain organization only. So we have, as the charge accumulates and as the deprotonation takes place, we have a change in the unit cell to one with much lower tilt. And we see a change in the domains as they start to progress towards more round domains away from this dendritic structure. The difference in the tilt between these two phases, which is 40 degrees and 33 degrees, so the less tilted being 33, the difference in the tilt corresponds to a chain height difference of about 0.3 nanometers, which is exactly what we saw by AFM. So what we think we have here, we have a new phase emerging in part, what we've proposed is that because this forms these condensed phases immediately upon spreading, that then as it deprotonates, this takes some time to happen. And that's why you have this slow rearrangement as it progresses from one phase to another phase. So we have a transfer via dissolution from the domain edges, which we have some AFM evidence for, a solution-mediated polymorphic phase transition, potentially via this liquid expanded phase that is present. So as I mentioned at the beginning, the one thing we wanted to do with this was to deposit it on gold, which means adding an omega thiolation. So we did an omega thiolation to the chain, and we compare the isotherms for our ODG, which is our octadecyl gallate, and our ODG-SH, and you see this shift to higher molecular areas. We thought that this might be the extended to bent conformation transition, right? So that in this case, the molecules adopt a BOLA conformation, but it's not quite big enough because it's been predicted using computational studies that for mercaptohexadecanoic acid, that bend should take up an area of about 65 square angstroms, which would be out here, which we clearly don't have. The other thing is that there is a slight kink here in the isotherm, and I'll come back to that, but that they appear to start to converge in area. So what we wondered is whether we're getting a BOLA, a mixed phase, so whether we have a combination of a BOLA form lipid and an extended surfactant coexisting. So we turned again to diffraction, and I think one of the things I want you to note with this is that, again, we have an invariance in that diffraction pattern. So this is the octadecyl gallate on water. This is the octadecyl gallate with the omega thiolation here on water also, and it gives us exactly the same diffraction pattern, which is quite telling that this thiol group, even the presence of a thiol group in the terminal, at the terminus of the alkyl chain, cannot disrupt the strong intermolecular pi stacking between the head groups. So again, we wondered if it was a kinetic process. So we, since two phases, if we do really have a BOLA form coexisting with a extended form, two phases should not exist over a broad range of pressures for a single component system. So again, we thought it might be kinetic. So we waited an hour again, and we shift much closer to where it would be predicted for a fully BOLA amphiphile. If we look at the Brewster angle microscopy, this is before equilibrate with a standard 10-minute equilibration after spreading. You see these large mosaic textured domains suggesting a high degree of anisotropy. And this is low and high pressure. If we equilibrate for 60 minutes, we get a few domains, but nothing very much, mostly uniform. But as we pass this now plateau, which appears exactly where there was a slight kink in the isotherm before, as we pass this plateau, we are able to restore this mosaic textured domain. And the height difference from AFM corresponds, again, we can push this to a homogeneous phase above this plateau, and we have domains below the plateau, and that height difference coexists very well with the coexistence between a BOLA form and an extended, which appears that over time it can relax. We can control this. So with time, it relaxes more to the BOLA conformation, but with pressure, we can force it back out of that and into an extended conformation. We play now a bit with pH, again, trying to force these head groups apart, trying to charge this. The first thing that you will see is that a pH 9, changing this to pH 9, basically is the same as equilibrating it for 60 minutes. So we can increase, we can add pH to this, so we can increase the kinetics of this, or control the kinetics of this interconversion using pH, time, and then be able to force it back using pressure. However, if we go to much higher pHs, again, 10 and 11, you start to see a much larger shift in the isotherm, again, to possibly to a fully Bola conformation. If we now look at the Brewster angle microscopy, we do see a very homogeneous phase, presumed to be a Bola phase. Few isotherms beginning to appear around 7 millinewtons just before that plateau. So this is at the pH 10. We also see these irregular shaped domains, which appear to have a degree of anisotropy. So it appears that they have a brighter perimeter and a darker interior, which we originally thought was an anisotropic effect. However, if we do AFM, what you see, in fact, is that we have these domains, we have these nodules of very bright, high material growing along the edges of these very frayed edge or very geometric edged domains that are appearing, which correlates well with these domains here. And that these nodules that grow eventually coalesce, but they never get beyond 1 to 2 microns in width. And at that point, after that, we start to see the growth of these filaments that appear that extend outward from the domain with exactly the same height. If we now look at the diffraction data at low pressure, so well below this plateau, there were no discernible peaks, which suggests that those few domains we had are just too low a density of our extended conformation to be able to detect it. At 5 millinewtons per meter, we had the same extended as we saw before with our 39-degree tilt. But at 15, what we see is a transition to a much less tilted phase, 15 degrees tilt, with no head group ordering. So again, we have no Debye-Scherrer rings, no additional peaks, no elongation of the full width at half maximum. And this is suggesting to us that we have a less tilted condensed phase, but that this higher material is an amorphous material. It does not appear to be crystalline as it was in the first system I showed you. So what we think is going on is that at very low surface pressures, we have predominantly our surfactant in the Bola form. At pH, so this is all at pHs greater than 10, just below the transition, we have that extended and 39-degree tilted phase that we've seen many times up till now. But as soon as we get above that transition, we have a much less tilted phase. We still have this background here. The height differences imply that we still have a Bola form. And again, this very regular height difference here. This is not a random height amorphous material. We've gone across many, many different images and domains, and it's always the same height, and it corresponds to effectively the same height as you have here. So it suggests we have a Bola on top, driven by strong head group interactions. So in our case, we have a Bola to extended interconversion that's reversible with time and with pressure, and the kinetics can be controlled by pH. And that phase boundary between the Bola and the extended nucleates a defined multilayer formation, which nodules that form a perimeter around them, they coalesce, but they always have this defined height and defined width. And after that critical defined width is reached, then you get this filamentous growth. And if anyone has suggestions for me on what is driving that filamentous growth, I would love to hear it. There have been some systems to which we can make some comparisons. So a phenolic bolus surfactant with symmetric head groups was shown to form filamentous domains, again attributed to these strong directional interactions between the phenols and between the phenols and the amides. And nanostrike multilayers have been reported also for another bulla, but in their case, it was driven by, as they proposed, by hydrophobic interactions between the chains, because the chain was upturned as opposed to the way we believe ours is. So with that, I see I'm running out of time. So let me tell you a bit about what we've been able to learn thus far. Our monolayers with pi stacking interactions all show a high degree of aggregation at these high molecular areas. So they form these very cohesive monolayers with defined structures immediately upon spreading. They're all rigid. I haven't shown the rheology measurements, but we have those as well, and they're all very rigid. We have done the compressibility, which I've shown you. They seem to have preferred head group orientations and directional growth patterns, which we believe from our computational studies are driven by pi stacking. I think it's quite interesting that the addition of the omega-thiol and or partially charging the head group does not always enough to disrupt those strong pi interactions. I fully expected the omega-thiol to break that up, to be able to disrupt that and force those chains further apart, but it didn't happen. We see multi-layers in both our systems. We have defined structures in terms of heights, both when the multi-layer is crystalline, but also when it's amorphous. And again, we see directional growth patterns along those striated boundaries in the first system, and here very highly controlled thicknesses and structures. And they're all reversible, but again, kinetically controlled because of those strong interactions. And with that, I'll finish. This is the work, the aminobenzoquinones was the work of our two undergraduates. Yuan Fang synthesized the material, but Shirin did all of the X-ray analysis. The phenolic work is pretty well all the PhD thesis of Renaud, with the computational studies by Janet, and the previous double chain lipids were studied by Ying Zhang. I obviously want to thank NSERC and CFI for the funding, and ChemMatCARS not only for the invitation to speak, but for the beam time that allowed us to work out these systems. So with that, I thank you.